Welcome everybody. In this video we will discuss about scalar electric potential and vector magnetic potential for time varying fields. For static electric fields we learned the relationship between electric field and electric potential. Electric field is the negative gradient of potential. The gradient vector can be interpreted as the direction and rate of fastest increase. Gradient of a scalar field is a vector. For a static magnetic field, the relationship between magnetic flux density and the vector magnetic potential is shown. The curl of the vector magnetic potential is equal to the magnetic flux density. By applying Gauss's law for homogeneous isotropic field, we derived the Poisson's equation for a static field as del square V is equal to negative rho V over epsilon, where epsilon is the medium electric permittivity, and del square vector A is equal to negative mu vector J, where mu is the medium's magnetic permeability. For different types of charge distributions, we came up with the solution of V. Expressions for V for a point charge, a line charge, a surface charge, and a volume charge are given, respectively, on the slide. Also, the expressions for vector magnetic potential for filamentary current, surface current, and volume current are given, respectively, on this lecture slide. We will find scalar Poisson's equation and vector Poisson's equation for time varying field in the next slide. The relation between magnetic flux density and vector magnetic potential will be discussed here. From Maxwell's equation for magnetic charge density of non-existence of magnetic monopole, we know that divergence of B is equal to 0. We also have a mathematical identity that says that divergence of curl of a vector is 0. For example, the divergence of curl of vector A is equal to 0. Now, if we equate Maxwell's equation, that is divergence of B equal to 0, and with divergence of curl of A equal to 0, then we can easily find a relationship between B and A. The relationship is the magnetic flux density B is equal to curl of A, where A is the magnetic vector potential, and the relationship is flux density, magnetic flux density is equal to the curl of vector magnetic potential. How electric field relates with scalar potential V and magnetic potential A will be discussed here. The circulation of E field is equal to the negative partial rate of change of B field over time, which is Maxwell's equation derived from Faraday's law. Substitute B with curl of A, we obtain curl of E is equal to partial over partial T curl of A. Then curl of E plus curl of partial A over partial T equal to 0. As the partial time derivative and the curl operator both are linear and independent, we can commute them, writing curl of partial A over partial T and changing the sign. Taking curl operator a common factor for both terms, we can apply another mathematical identity that says curl of gradient of any scalar is equal to 0. For example, curl of gradient of negative v is equal to 0. So as electric field is emanating from a source, we can take a negative sign that is also consistent with the static case. Now we get curl of electric field plus partial A over partial T equal to 0, and also curl of negative gradient of V equal to 0. Now equate these two equations, we will get E plus partial A over partial T equal to negative gradient of V. Now we solve for E field is equal to negative gradient of V minus partial A over partial T. This is the relationship between electric field with scalar electric potential and vector magnetic potential. Let us consider the Maxwell's equation saying the circular magnetic field includes a current density J and a partial D over partial T, replacing H by B over mu and then multiplying both sides with mu, we obtain curl of B is equal to mu J plus epsilon mu partial time rate of E for homogeneous isotropic linear medium. Substitute B with curl of A and E with the expression that we have derived in the previous slide. Apply vector identity to expand curl of A. Take the second order term to the left side of the expression. Then multiplying both sides with a negative sign. At this stage, we set the factor epsilon mu partial V over partial T plus divergence of A is equal to 0, meaning that divergence of A is equal to negative epsilon mu partial V over partial T. This assumption is called the Lorentz condition. The Lorentz gauge, by dint of the principles that we are free to choose the divergence of vector A to be anything we want without changing the system's electromagnetic physics. If we apply Lorentz condition, we obtain del square A minus epsilon mu partial square A over partial T square equal to minus mu J. This expression is called the vector Poisson's equation for time-varying fields. Considering Maxwell's equation obtained from Gauss's law saying divergence of D is rho V, applying constitutive law D is equal to epsilon E. Replace E with the expression obtained before and also dividing both sides of the expression with epsilon if the medium is homogeneous, linear and isotropic. We get del square from divergence of gradient of V and replace divergence of A with the Lorentz condition derived above. The mathematical work leads to the scalar Poisson's equation for time-varying field. If you observe the vector and scalar Poisson's equation, you will notice that they are decoupled. The vector Poisson's equation solely depends on magnetic field term like A and J, and the scalar Poisson's equation solely depends on the electric field term like V and rho V. Unlike electromagnetic Maxwell's equation, where the electric field and the magnetic field are coupled, the scalar and vector Poisson's equation are called the wave equation in terms of vector magnetic potential and scalar electric potential respectively. Solutions to the Poisson's equations are shown in this slide. The expressions are similar to the expression that we already have obtained for the static case, because the del square term is very same in both static and time varying cases. But in time varying case there is another second order partial derivative term that should incorporate to the solution. It is done by putting a square bracket in the charge density and current or current density term. The meaning of the quantity in a square bracket is that the term is delayed by a time t prime, and the term is called the retarded term. Sorry for choosing such word. The retarded time or delay time or propagation delay time t prime is equal to t minus the distance between the observation point and the source point divided by the speed of propagation. In free space, the propagation speed is the light speed, that is equal to 3 times 10 to the power 8 meters per second. I will repeat the work in frequency domain. We start with Maxwell's equation, divergence of Bs equal to 0. We also know a mathematical identity, that is divergence of curl of any vector is equal to 0. Now if we equate these two, then we can write that curl of As is equal to Bs. We take another Maxwell's equation, curl of Es is equal to j omega Bs, where I replace this Bs with curl of As and move to the left side. And we also can take another mathematical identity that says curl of gradient of any scalar is equal to 0. We multiply this with a negative sign because right hand side is 0, and we equate these two equations and we say that Es plus j omega As is equal to negative divergence of Vs, and this is the relation between electric field and potential. Now I take another Maxwell's equation, curl of Hs is equal to Js plus j omega ds. Then we replace Hs with Bs and ds with epsilon Es. We are replacing Bs with curl of As and then expand this curl of As and replace Es is equal to delta Vs minus j omega As, since they are sides, and we assume that delta of As is equal to j omega epsilon Vs, that is called Lorentz condition. And if we introduce this Lorentz condition in my equation, you will come up with the vector Poisson's equation. Now I take the divergence of ds is rho Vs, the another Maxwell's equation. Use the continuity equation ds equal to epsilon Es. Then for homogeneous isotropic medium, we can take the epsilon to the right hand side. Then we replace Es with the expression we found before. Then we expand this and we get the W square Vs is equal to j omega divergent of As equal to negative rho Vs over E. Apply Lorentz condition and it will come up with the scalar Poisson's equation. We sum up the work in frequency domain here. So we find frequency domain vector Poisson's equation and frequency domain scalar Poisson's equation.